Hi, my name is Chris Heistand, and I am the flight software architect at Stoke Space Technologies, and I am going to present When Flight Software Gets Grounded, Gaining Efficiencies from a Ubiquitous Software Stack. So today I'm going to try and walk through what is vehicle software and why am I presenting at a flight software conference. How is it used, vehicle software hierarchy and taxonomy, show you a little bit of the software in action, and go through pros and cons of the consolidated stack approach. So what does it do? What is vehicle software? So to us, vehicle software is it's that loop on the left. So you basically you need to sample data, control based on that sample, output based on the control, and then ship telemetry. And so this is a very simple input, process, output loop. But that is, at the end of the day, what we have consolidated vehicle software to mean. And that's the same on the flight software. That's the same on the ground software. You have one loop to control them all. So vehicle software in Stoke terms is anything that is dealing with this real-time loop structure. We have a bunch of constraints for that, so we need it to be robust. Vehicle software is used on the test stand. It's used on the vehicle. It's used for development. If something goes wrong in vehicle software, engines can explode. And so we need that software to always work in a reliable fashion. We have a distributed and isolated system. So we have multiple targets that we are deploying this loop to. So we can have multiple targets working together. And we also have the need for the rocket to be able to fly away and not have to talk to ground and be able to do its own thing. So we have a distributed and an isolated system. We have the need for human and computer control of all of this software. So the human on console needs to be able to click buttons, open, close valves, be able to read telemetry and understand what's going on. And then we also have computer logic, where we need to be able to do thrust vector control and tank control and other automated actions that are in that control logic block. We need it to be highly flexible. So we are using this not only on the vehicle, but we are using this on our test stands. We are using this on our development acceptance test and thermal chamber systems. So we need to be able to flex to a whole bunch of variety of different pieces of hardware, of different setups, of different rates, and we'll get into a lot of that later. We are running this loop from 20 to 100 hertz. So we're going and input, process, output, ship at a certain rate. But we are also sampling it at much faster rates than that. So we can sample one piece of data for each of those cycles, or we can sample thousands of pieces of data. And so we have the need for that kind of dual rate concept. And we're pushing a lot of data. So we're talking 10 to 500 megabits per second of data, depending on the target and depending on what we're actually sampling. And the last thing, it needs to be everywhere. It needs to be ubiquitous. We have a really small team, and trying to build more than one of these, whether it's for a test ops thing or whether for its developmental testing or however it is, we only have bandwidth to build one. So it's got to be everywhere. It needs, by requirement, it has to do all of the things. So where and how is it used? Well, anywhere we are sampling or controlling a real-time system. And that's like, period. There's if we are doing software development, it's on the same stack. If we're doing hardware development, it's on the same stack. If we're doing acceptance test of hardware, it's on the same stack. If we're doing hardware testing, it's on the same stack. If we're testing a thruster out at Moses Lake, same stack. If we're doing launch ops, if we're doing vehicle ops, if we're doing anything with the engine, it's all running the same exact vehicle software stack. And that is really the thesis here that I want to try and show how that works and why that works. So to explain kind of how it works, let's go through the hierarchy. First, we have a thing called a system. A system is a collection of targets. So you can see on the right here, there are 3 flight software targets, 1 ground software target that are kind of like built into this system. So that's 3 different instances of that loop running. For flight software, 1 instance of that loop running for ground software. All of those are sampling, processing, outputting, and then telemetering data. So a system is a cohesive set of those that makes up one of our either a test stand, a test setup, a rig, a developmental setup. So we have a component container stand where we are doing individual component testing of thrusters or of pump parts. We have a thing called second stand, which is our second stage test stand for our engine, which is running the same software. And we have hardware in the loop, which is, again, running the same hardware, same software. For a system, it is an atomic build deployment, a scoped namespace, and a scoped network. And basically what that means is that everything within that circle boundary here is one stamp, one cohesive unit that is all being built together, deployed together, and kind of like used to answer one thing. This system can go and test a power distribution unit. This system can go and test a thruster on the stand. And really what you get out of that is that you don't have any schisms between ground software and flight software. So there's no chance of a telemetry or a commanding mismatch between your I'm trying to run a sequence, but my packets don't line up. We can have overlap in namespaces and networks if we're going from something like a thruster test to an engine test where we're using 15 of these thrusters. So all of a sudden we're able to actually split that out and have the same names and same processing and same visualization tools because it's named thruster 1, 2, 3, 4 here, and it's named thruster 1, 2, 3, 4 here. And we have a console on the outside of the system that takes in the system configuration, says, hey, these are the things that I have access to. These are the things that I can click and open and close and visualize. So at the end of the day, you still have to build up your UI, and that becomes rather specific. But from a system perspective, you are totally closed off from the rest of the world in as far as namespaces are concerned, and you're not worried about collisions, and everything stays consistent. A system delivers an end-to-end capability with a handful of targets. So targets are the software runtime. So think about each one of these as a piece of hardware where flight software or ground software is running on. So it is basically a key value store with a bunch of modules attached. You have a super loop that is running that input, process, output. Super loop, it is C, Rust, or Python based. And we have a JSON file that kind of defines everything. So like unpacking that, we have one big key value dictionary that you can go and access sets and gets, which is the entire state of one of these targets. Modules are attached and added to the overall target so that you can access IMU, for example, or access a new DAC. And what happens is we go through and we take all of the inputs from all of our modules, we process everything from our modules, and then we output from our modules, and then we ship telemetry. And so you have that kind of like very simplistic walkthrough of that circle, that data circle, that you end up, it's very easy to be debugged because you know if something happened here and something weird is looking here, you can actually tell exactly where that happened. You're not going and diving into any sort of event-based structures, any sort of information there, and you have the state of your entire system at all times because everything is using this key value store. Each one of these targets can run at whatever rate you specify with whatever modules you specify. And so that's where you get into that JSON defined loop structure. The actual binaries get deployed to the individual pieces of hardware that are running Linux. And they all get deployed simultaneously, like we talked about with systems. Then we get to the sensor and actuator list. So you can think about a target, and the target JSON is defining the overall larger parts of the system, larger software modules that are required to actually interact with things. And the sensor and actuator list are all of the individual channels, like this pressure transducer is connected to this slot on this stack. And so it's the what is connected list for channels and scaling. We define what servos exist, the pressure transducers, solenoid valves, thermocouples, power services, all of those individual mappings are defined in this one place, this one-stop shop for sensor and actuators. We also have scaling per sensor, so this is an as-built list, and this thing changes daily. So the test team that is using the system that you see here is changing actual hardware, connecting different sensors into different channels, and rearranging different pieces of the DAC, adding servos, changing actuators, all of that daily. And they're expecting a 10-minute turnaround from the hardware actually changing to the map changing, and then the software being able to read in all of that data and then produce it in whether that's in console or data processing, or be able to control it with the sequence. So there's a lot there that you have to flex on in the sensor and actuator list. That really that's one of the key pieces that we had to answer. And from a test stand perspective, is needs to be very flexible. And from a vehicle perspective, it needs to be a lot more static. And we'll talk about that in a second. So software in action. So yeah, cool, whatever. We made a single software stack to rule them all. What does that actually mean? So we have component containers basically what I want to show you is 4 different versions of the same exact software source being used with different configurations, different hardware, different use cases across the company. So we're running in the top left, we have a component container for thrusters. So we have two targets of flight software connected to a ground software target out to console, and then everything's being streamed out to data so that people can actually review it. On the right, it looks exactly the same. It's totally different hardware, but it looks exactly the same, just with a different configuration for the stage 1 stuff. When we get into the second stand for our actual engine testing, we have a little bit more, another target is involved. We have a more configuration, but again, exactly the same. And then we have kind of this special thing that we did as a one-off test called Rocket Car that I'll talk about at the end. So component container. When we were originally coming up with this concept, we needed to be able to answer everything from testing an individual piece of hardware all the way up to testing the rocket. The software needs to be the same. The hardware needs to be the same. The way that we interact with it needs to be the same. So 2 flight software targets, each running that input process output loop. They're running at different rates. Talking to ground software. Ground software is holding on to sequence and sequence logic. Talking to console. You can have as many consoles as you want, just like kind of looking in. And all of that data needs to be streamed to a data processing API, and all that needs to happen in 5 minutes. So what's a test actually look like? So this is the component container with a second stage thruster. So an individual thruster, we have 30 thrusters on our actual engine. So this is acceptance test of one of them. We have flight software controlling, we have ground software running the sequence, we have an operator on console, and then as soon as the test ends, all that data gets shipped out through the data API, and people are able to review. Cool. So what happens when we want to completely and totally change hardware and test a wildly different concept, like a stage 1 aux preburner for our turbo machinery? Well, the software sure does look the same, because from a source perspective, nothing changed. From a configuration perspective, one file changed. From a sequence perspective, they wrote a completely different, they just like wrote their own sequence for handling the aux preburner, which was just a different, interacting with totally different keys. And then from a console, the longest part of all of this from a software perspective, whenever they went and added a stage 1 container, was building up the console. So from a software perspective, we're talking 5 hours of work, 4 hours for the console, under an hour for configuration. And then we were able to actually start getting into iterations on real hardware, working out the kinks of, oh, well, we really want this sensor, not that sensor. And so last December, right before Christmas, we got to have our first aux preburner test fire, which was incredibly exciting, and just another kind of proof in pudding thing of, well, that's the same exact software. When we move to a totally different stand, we have a whole engine. So that's right now it's 15 thrusters, not 30, but 15 thrusters on the stand with turbo pumps, the whole 9 yards. We have 3 targets, so 3 different deployments of flight software input, process, output. Each one of these are running their own loop. They are talking to ground software, same sequence engine, talking to console, same console. And what you end up with is the operators that are working on the component containers know exactly how this all works, because it's the same thing whenever they're running on second stand, just different sequences, different configurations, different keys that you can go and access. One thing that was a little wonky that we did was, okay, so that's fine and dandy when we have full test infrastructure and test ops and teams out there that are doing things that are a lot more regimented. Anytime you deal with fluids, anytime you deal with cryopropellants, you need to be incredibly safe about everything that you do. So that has a lot of planning and is very involved. Well, we also need to do avionics testing on our own and GNC testing on our own. So we came up with a concept where we were shipping all of the avionics out from Kent, Washington to Moses Lake, Washington. We're going to drive through the mountains. It's a nice 3-hour drive. What happens if we just like turn on the avionics and we're able to log and process for a nav test the entire way? So we did that. We took out the ground system hardware. We threw the ground software target, so like the actual software binary, onto one of the flight software computers. We accessed it through a command line interface. It's just keys that you're setting and getting from our laptop. And when we plugged it in, we went through the same data processing API, and everything looked the same. So at the end of the day, this is what we had. We shoved our avionics and got a full test of power all the way through the system. GNC being tested from a nav perspective. We were able to test out our GPS, our IMU. We were able to test out GNC internal state measurements, and all of this from a laptop with whatever pieces that we had, and we were able to kind of downscope either the flight software or ground software or any of those needs, because it's like that. It's built to be that kind of flexible system where you just change the configuration and redeploy. So definitely some pros and cons here. The vehicle software team is critical path to like every single user. Anybody that wants real-time data, anybody that wants to interact with a mechanical system and control it, anybody that is testing or tank proofing or doing some sort of development with in avionics, it's our stack that they're using, and it's so that becomes very taxing from a support request perspective, and you have to be ready and you have to continue to be committed, because there will always be times where somebody's like, but I could just do it this other way, it would be so much easier. But as soon as you branch and people have their own way of doing things instead of a consolidated way that everybody is using, you lose a lot of efficiencies down the line. It's really, really easy to be tempted by that immediate thing, so the vehicle software team can be off the hook. But you really lose a lot there. You end up having a superset of regulations, requirements, and verification. So everybody, whether you're doing dev or whether you're doing vehicle, is using the same software. You have to deal with the same regulations and the robustness needs, whatever kind of verification we're using. And so it has to kind of be, you end up at the highest level of need there. You have a flexibility continuum of needing to flex from the test stand needing to be able to change things in 10 minutes to the vehicle needing multiple subsystems and subteams to all have very reliable kind of change sets that they know exactly what's going on at all times across multiple teams. And so that flexibility is hard. And it really demands a commitment to vertical integration. So you have to, as a team, as a company, the avionics team has to have the same hardware as the test team. The ops for vehicle has to look has to work in a similar way as the ops for the test stand, as the ops for acceptance testing of individual hardware components. And so you're kind of like helping shape all of that, but all of the teams have to agree, and you kind of like build this fabric of dependencies against each other. So that's actually a pro. When you have a dependency fabric of flight software is reliant on hardware on the avionics team, and the avionics team is dependent on the flight software and vehicle software, you have to grow together. And it forces a lot of team communication. It forces a lot of team understanding and descoping of any sort of frivolous stuff, because everybody has to work together in lockstep. So that forces commonality, that forces scope discussions. Everybody's giving you immediate feedback. As soon as something breaks, you will know because everybody's using it. We have hundreds of hours of runtime of like live fire runtime on our software already, and we have not launched yet. To the point of the integration piece, we don't have integration jumps because everybody is taking those small pieces, and if flights like vehicle software needs something from avionics, you find out super early, and everybody does have to grow together. And so that is extremely helpful in being able to say, hey, test ops have been happening for the past 6 months. We're getting into vehicle ops now. Oh, it's the same thing. It's the same software. It's the same console. It's the same interactions, the same sequences. Everybody has already learned that system. So there isn't a big switch over. There isn't like, oh, well, now we need to go figure out why this integration piece isn't working, or why these pieces of hardware are acting differently under one software scheme versus another. It's all the same, and it's always been the same. So it truly has given us a huge amount of benefit, just forcing everybody to move forward together. Thank you. That was my talk. I hope that it was interesting. if you have any questions, then ping me on the Flight Software Slack and or email at me at chris@stokespace.com. And like everything at Stoke, everything is something else. So we're thanks Tim for the quote. So we're really excited for what comes next and what we can use this software for next. Bye.